Okay, so identifying redox reactions, is in like which balance equation represents a redox equation. So how do you know if you're looking at a redox equation? Well, redox, did something get reduced down and did another thing get oxidized up? Did those two things happen? Then it's a redox reaction, because not everything is. So an example of something that's not is this. And again, how did you figure out if something was reduced and oxidized? You assigned oxidation numbers, and then you saw did they go up or did they go down. Sometimes they do neither. Like if you were to assign these numbers, and I'm not going to take forever and like show you each number, but if you were to look at them, that's +1, that's -2, that's +1, that's -1. Na went from being +1 to +1. O went from being -2 to -2. H went from being +1 to +1. CO went from being -1 to -1. Nobody changed. Nobody got oxidized. Nobody got reduced. Everybody's charge stayed the same. And that is what tends to happen in double replacement reaction because everybody's like in a new couple and they've kind of like regained their charge with somebody else. How to identify redox reactions? Well, you have to assign all the oxidation numbers, inspect the oxidation numbers, figure out did somebody get oxidized up, did somebody get reduced down, but there are a couple of shortcuts. One of them is double replacement reactions are never redox reactions. Always get their charge back. The next hint is that single replacement reactions are always redox reactions. So that's my quick way that I always try to find the redox reaction in one of these questions like this is by looking for the single replacement. So let's talk about why they're always single replacement. All right, so why are single replacement like pretty much always redox? Well, let's look. Okay, zinc is a 0. This is +1. This is -1. H is alone, so it's a 0. Then this is -1. There's 2 of them, so this is +2. All right, so I assign the oxidation numbers, and then I go, oh, zinc, you went from being 0 up to +2. Your charge went up. You got oxidized. H did nothing. No, H did. H went from being +1 to 0. Its charge went down. Oh, you got reduced. So see how those zeros kind of always make it so the charge changed? Like if you have a single replacement, you had a single guy who's now in a couple. That means he went from being charged to, from being 0 to being some sort of charge. Or here you have a single guy and he was in a couple. And that's the definition of a single replacement, right? There was a single guy who broke up a couple and is now in the couple. So if something went from being alone and 0 to now charged, that is like definitely going to be a redox reaction because it's changing in charge and it's either going up or down. One goes up, one goes down. One gets oxidized up, the other gets reduced down. So when I see a hard problem like this one below, so I see a hard problem like this where they're like, which balance equation represents a redox reaction? And I'm like, oh my God, the way to figure out redox is to assign oxidation numbers. Like, I don't want to assign oxidation numbers to every single part of every single one of these. That's going to be so annoying. So what I do is I take a shortcut and I go, oh, well, all single replacement reactions are always redox because you always have a single guy who's a 0 who's now in a couple with a new charge. And you had someone who's in the couple who's now a 0 in a charge. So somebody's charge went up and somebody's charge went down. So what I do for these is I just start looking for a single guy, single replacement. And I'm like, no, these are all partners. These all have partners. Here I've got a single guy and a couple, and then a new couple and a new single guy. I've got a single replacement reaction. I bet that's my redox. Let me assign charges and check. Yep, it is. All right, somebody got reduced down. Let's see. H was +1, and now it's alone, so it's a 0. So H got reduced down, and I bet somebody got oxidized up. So Mg was a 0 alone. Now it's the first thing in a couple, so it's positive something. So its charge went up, so magnesium got oxidized up. So again, how do you figure out if something is a redox reaction? You need to have somebody who got reduced down, somebody who got oxidized up. So you're going to figure that out by assigning their little charges or taking a shortcut and looking for that single replacement reaction. Okay, this is just a reminder that oxidation is loss, reduction is gain of electrons. This oxidizing and reducing agents is interesting. Maybe we'll circle back to it. It's not that hard. I just don't know if I'll have time for it. So for now, we're going to skip it. And those are my lovely children. So just the one more thing I want to tell you for this section is, why do you hear that word oxidized but we haven't talked about like if something is left out in the air, you say, oh, it got oxidized. Like if you peel an apple and then you don't eat it right away and it starts to turn brown, or if you cut an apple and you don't eat it right away and turn brown, or an avocado, or they say like, oh, the air got to the bread. Like if you didn't seal the bread up all the way, it starts to get stale, and they always like blame it on the air. So when you hear the word oxidized, you think of like air and oxygen, and it's like, why have we not been talking about that? What I will say for that, and the fact that we skipped the oxidizing reducing agent kind of makes it difficult. Actually, never mind. So basically, whenever something is oxidized, oxygen is really good at getting reduced. So whatever comes near oxygen, oxygen is good at getting reduced. It's good at taking electrons. So when oxygen is near something, that thing tends to get oxidized because oxygen's really good at getting reduced. It's really good at stealing electrons. So if you're near oxygen, you may very well get oxidized, which maybe that's where the term oxidized comes from. Oxygen might steal your electrons. So if you're a piece of bread that gets exposed to air, the oxygen is probably going to steal your electrons and oxidize you and make you get stale. If you are a cut apple exposed to air, the oxygen is probably going to get reduced, steal your electrons, and cause you to get oxidized. If you are a car exposed to air and water, if you're the car, the oxygen around is really good at getting reduced, going to steal electrons and cause you to get oxidized and rust. Okay, so that's where that, like, if you've ever heard something is oxidized when it's exposed to air, that's where that comes from. So it's just that oxygen is really good at getting reduced. So it's really good at causing other things to get oxidized. It's not the only thing that causes other things to get oxidized, but it is very good at it. So we do call it a good oxidizing agent, which is the thing we skipped. So here's just one good example question I found. When aluminum is exposed to air, forms a protective layer. Like when you leave aluminum out and you see that like layer of gook on a metal, what's happening? Well, that is getting oxidized. So when something's left out and exposed and kind of something bad happens to it, or it starts to form like some stuff on it, or rust or brown stuff, if it's like an apple, that's it getting oxidized.